Okay, what we'll do today is finish up soils. This last part's super simple and quick. And then we're going to move on to energy. So I told you the semester is kind of going to be a bunch of water early and then energy. And then we'll come back to a couple topics near the end that kind of combine both. Okay, especially oceans and desalination. So let's just finish this up. So we talked about soils the last few classes, how they form, how they develop these various horizons, different ways you can classify them, properties that they have like liquid limit, plastic index, and what that tells you in terms of how they will react when humans disturb them. This last classification is probably the most commonly used. I'm going to have a lab coming up for you on soils, and this classification is one that gets talked about pretty heavily with most soil scientists. And it's pretty simple. It's the U.S. Department of Agriculture classification for fine soils. And it's based on the percentages of sand, silt, and clay. And last class I gave you kind of the definitions for sand, silt, and clay in terms of size. Basically what you do is you put these soils in a stack of sieves that have various size openings, and you shake the soil around until all the sand ends up in one sieve and all the silt ends up in another sieve and all the clay ends up in the bottom, and then you simply look at the proportions. And the way this works is you get different soil types depending on the percentage or the proportions of sand, silt, and clay. So here's an example. Let's say we have a soil that's 40% sand, 40% silt, and 20% clay. So if you start with, let's say, 40% sand, the way they're called ternary diagrams, ternary for three corners. So at the very top is the clay corner. So if you were right here at the apex, it'd be 100% clay. Okay? Down here is the silt corner. If you're in the lower right corner, it's 100% silt. And if you're over here in the lower left, it's 100% sand. So sand, let's say we started in this corner. Okay? It goes from 100% here, and if you're on this line opposite of it, you have no sand. Okay? If you were, let's say, right here at the midpoint between 100% silt and 100% silt and 100% clay, this would be 50-50 silt clay with no sand at all. And as you move closer, you get more and more sand. So here's the 50% sand line right here, and this is where 40%. Okay? Then you move on to silt. And we have 40% silt. Silt's in the lower right corner, 100% here. 0% is the line opposite the corner. Here's the 40% line here. You can see they're already intersecting at two places. And if you finally put your clay in there at 20%, 100% at the apex, 0% at the bottom line, there's 20%. They all converge on a single point, and that is called a loam. Slightly higher percentage of clay and slightly less of sand and silt, and you may end up with a clay loam. If you're anything above maybe 50% clay, it's just called clay. Got sand in one corner, silt in the other corner, and various combinations thereof. And remember, we talked about having a nice mix of particle size, made your soil strong. So the soils that kind of plot in the middle, where you have a nice proportion of each, those would be pretty strong soils. If you're down at the corners, they're actually pretty weak soils. Pure clay tends to be pretty weak. It also tends to be really sensitive and have a really high plastic index. Clay is just bad. It shrinks, it swells, and it loses its strength really easily. It's terrible crap to build on. Sand isn't so great either. It's all single size. There's lots of space between the sand grains, so it's not touching in as many places as it could. It just doesn't have the internal friction to be a good, strong soil. So that's how you read the chart. And I'll give you one of these charts so you have it in your notes. Any questions on how to read that? Okay, cool. That's all I have for soils for now. We'll follow up with the lab in a couple weeks. All right. As promised, we're going to move on to energy. I want you all to take the next minute, and I want you to write down your definition for what energy is. This is one of those classes where I'm going to challenge you on words that you know, but maybe you don't know all that well. We use the term energy all the time. I have lots of energy. Well, what the hell actually is energy? What do you mean? Okay, energy, a term you've all used many times in your life, right? Was it easy to come up with a definition? What did you come up with? I'm not expecting it to be right, if there is right. Yeah.
Movement of an object to create a source of power.
Movement of an object to create a source of power. That is one of the more interesting definitions that anybody's come up with, because we're actually going to talk about pretty much every term you just had in there. Power, work, object. So in your definition, you have to move something, right? So under his definition, if I just sit on my ass right here, am I working? Am I using energy? How am I using energy? Let's say I'm just gonna be motionless here. I'm even gonna shut my mouth, which is rare, okay? So I'm just gonna sit here. I'm not gonna move. But I'm gonna eventually, if I just sat here long enough, right, I'm gonna die. I'm gonna burn up all my energy stores, I'm gonna dehydrate, I'm gonna be dead, right? So something's happening, right? Inside of me, what's going on? Heart's pumping, right? There's all sorts of crap moving on in there, right? My heart's pumping blood, right? I've got synapses firing, hopefully brain cells working. That's not a given, but you know, we'll assume some of that's happening. So inside I actually have some stuff going on, even though I can sort of hold myself motionless, right? What else do you got for definitions? Even if they suck. Sometimes the suckiest ones are the best. Anna, I know you want to say yours.
I said something that creates power through a process or reaction.
Creates power? Okay, you use power too, right? What's power?
You just have to know power.
Just power, right?
You have to know it.
Well, what would it, give me an example of something that's powerful. Superman. How is Superman powerful? He can do what? Strong. He can, and strength is manifested how? He can lift big things, right? He can move quickly. Okay? So power, work. Here's the physics definition. Okay? If we go talk to our brothers and sisters over in the physics department, They're going to say that energy is the ability to do work. So what do you want to know next? What is work? Okay? And yes, our physics brothers and sisters have a definition for work. And they have a definition for power. Okay, so physics is the ability to do work. All right, let me give you the definition for work first. All right, I asked you a minute ago, am I working? Well, if I sit motionless, it doesn't look like it, right? But I have all this stuff going on inside. My heart is beating. I've got chemical reactions going on, keeping me alive. So there's lots of stuff going on inside. And actually that fits the definition of work and energy use, okay? So I'm at the point where my body might be working even if it appears to be motionless, right? And we know it's consuming energy. So all these things are related. Movement. Think of it this way. Let's say I had a rock up here, right? And I slowly pushed it. It took me 10 seconds to push the rock from this end of the table to that end of the table. If I had more power, what would change about that? The speed, right? How quickly I was able to move things, okay? So we might be able to define a few of these. All right. Before we get to these definitions, just based on your definition of energy, think of 5 ways that you use energy. Maybe every day, maybe once in a while. If I just sit here and think, am I working? Yeah, I'm not really moving, but something's going on in the brain, right? There's electrical pulses that are happening, so all that's requiring energy. All right, what kind of ways do you use energy? Sleeping. When you're sleeping, your body keeps doing things, right? You have dreams. You know something's happening, right? What else? How else do you use energy? Driving. What's the source of energy for you to drive? What's the ultimate source? What's providing your car with energy? Gasoline, diesel, some sort of fossil fuel probably, right? How else are you using energy? Eating, okay? What gives so your body has some energy, right? I can do things, right? You can do things. What gives our body energy? Food, right? Okay? So we feed our body with an energy source. Food is our energy source, right? We feed our car with fossil fuels. That's its energy source. You guys plug stuff in, right? Cell phone, computer, whatever electronic appliance. Electricity is an energy source, right? So we have different sources of energy that allow us to do things, okay? So I want you to, as we go through this, to think about what we use as energy sources and whether we have different kinds of energy. I mean, obviously we do. We have food energy. We have fossil fuel energy. We have electrical energy. Does the sun give off energy? What's the process in the sun that gives off energy? You guys know? Yeah, it's nuclear fusion, right? Okay, so we have nuclear energy. So we have lots of forms of energy that allow us to do things. Okay, so we're going to get into some physics definitions. So we're going to go back a little bit. We've talked about most of these. Mass is stuff. Mass is atoms. Okay? We measure mass in grams or kilograms. Weight is similar. Weight is actually the attraction of mass to a gravitational source. So over on the left there are a bunch of rocks, right? So those rocks, I could have them here on Earth, right? Let's say one of those rocks over there weighed 2.2 pounds, okay? Let's say I moved that exact rock to Mars. Does the amount of stuff in the rock change if I move it to Mars? No, that's the mass. We measure mass in kilograms. So here on Earth, if you take a kilogram and put it on a scale, it's going to weigh 2.2 pounds. That's the attraction of that mass to the Earth. So 1 kilogram attracted to the Earth is going to weigh 2.2 pounds. If I take that same kilogram to Mars, I still have the same size rock, right? Still the same mass. It's still going to be a kilogram of mass. But it's going to weigh about a half a pound. Because the gravity isn't attracting it as strongly. So mass is the amount of stuff measured in grams or kilograms. That's not going to change depending on where you are. But the weight might, depending on what body that mass is being attracted to. So mass and weight are related but different. Weight is the effect gravity has on mass. So on Earth, 2.2 pounds is the gravitational attraction of a kilogram of mass to the Earth. If we go to Mars, it's not going to be attracted as strongly. The weight will be less, but the amount of stuff there is the same. If you have no gravity, you could take that rock out into space, right? It's still a rock. Still has all of its atoms. It's still a kilogram. But it's going to be weightless. It's not going to be attracted to any particular center of mass. And like we said, 5 kilograms or 1 kilogram or whatever kilograms on Mars is only going to be about a third of what we have here on Earth. So you think about it, you go to the moon or Mars where there's less gravity, you're still as strong as you are here, right? Your legs are as strong. You should be able to jump quite a bit higher on those planets than you should be able to here. You've got just as much power in your legs, but gravity is not going to fight you as much. And this is something you guys should just know this. It's useful. 1 kilogram is 2.2 pounds. If you go to countries that use the metric system, you'll see like a half kilo of ground beef and a half kilo of chicken. It's about a pound. 1 kilo, a little over 2 pounds. Mars has about a third of the gravity, and as you calculate it out, things weigh about a tenth of what they do here on Earth. Okay, so mass and weight, sounds like you guys got the difference. No problem. Force, okay? This little bottle of hand sanitizer has some mass, right? If I let go of it, it's going to fall to Earth. And at first it's going to move slow when I drop it, and it's going to accelerate. It's going to go faster every second, okay? If you jump out of an airplane, I don't know if any of you have been skydiving, those first few seconds are pretty amazing. You feel the acceleration. You can feel the drop, right? And if there was no atmosphere, you would continue to speed up all the way until you augured your body into the Earth, okay? You would go faster and faster. Every second, you're going to increase your velocity by 9.8 meters. That's 30 feet per second faster every second. You know, 30 feet is Here's the back of the room. So first second, you'll go that far. Second second, you'll go twice that far. Third second, you'll go 3 times that far. So you're just going to keep accelerating. Now what happens on Earth when you jump out of an airplane is you have all this atmosphere around you, and the atmosphere actually pushes back on you. And you end up reaching something they call terminal velocity, which is 200 and some miles per hour, which is pretty damn fast. But, you know, if there wasn't an atmosphere around, you'd just keep accelerating. So accelerating is the change and the increase in speed over time. So force is a mass times the acceleration, okay? So this is half a kilo, about a pound. Acceleration is 9.8 meters per second squared here on Earth. 1 kilo times 9.8, your force would be 9.8 newtons. You can go back and do the calculation. We talked about stress. We've talked about stress a bunch of times. I always use the flat-soled and high-heel shoe example. I weigh about 70 kilos. Gravity is going to pull me down at 9.8 meters per second squared. 9.8 is almost 10. 10 times 70 is 700. So if I stand here, I'm putting about 700 newtons on the floor, okay? Now, I have flat-soled shoes on the floor. They have a surface area that, you know, maybe better part of a square foot if I put my feet together. But if I just stood on 2 high heels, you're talking about a surface area that's really tiny, right? So when you have such a small surface area in an equation like this, you end up with an enormous amount of pressure. So even though the force is the same, the area over which I'm applying it is much different, and the pressure is much different, depending on whether I have a big broad area that I'm standing on or a really small area. And for the last test, we talked about hydrostatic and lithostatic pressure. That's the pressure of being buried by water or rock. So if I bury you 10 meters down in the ground, you're going to feel some pressure. It'll be less pressure than if you got buried 100 meters under the ground. And it depends what's on top of you, whether it's styrofoam popcorn or ball bearings. So we had density times gravity times depth. Okay, so back on the first page of notes, we said that the physics community defines energy as the ability to do work. We talked a little about work. Physicists have a definition for work, and it's force times distance. So some of those mid-sized rocks over on that table over there are probably about 10 kilograms, around 20 pounds. In order to get those to move, you got to push on them, right? Work is force times distance. So if you push it 10 feet, you're doing some work, right? If you push it twice as far, you're doing twice as much work. Okay, I'm pushing on this tabletop. Table moving? Am I working? Sure feels like I'm working, right? But according to this definition, has the table moved any distance? So according to this definition, I'm expending energy, right? But am I doing any work? According to this, no. Physics is the ability to do work. It's not. Energy is the ability to do work. Ability to do work. Doesn't mean you actually do work and expend energy. You can sit here and expend a lot of energy and get no work done. In reality, if I push on this, maybe it's moving a tiny amount, Maybe if I push on it long enough, I break enough bonds in the support structure that it lets go, and I'm able to do more work. But definition, really simple, force times distance. Push 10 kilograms, 30 meters. All right, using this definition and what we've talked about so far, what is power? What would power be? All right, think of the example, pushing 10 kilograms, 100 feet. Give me a powerful example and a not powerful example of doing that. I could do it powerfully, right? And I could do it not powerfully. What would be the difference?
The time.
The time.
Yeah.
Yeah, so power is simply work divided by time. How quickly we use energy to do work. Let's say I have a 10-pound box. I could push that 10-pound box 1,000 feet. That's working, right? You're applying a force. It moves a distance. But I could do that really quickly in 1 second. It's actually really hard to do. Move a 10-pound box 1,000 feet in a second. You'd need an awful lot of power to do that. If I did it in 10 seconds, I'd be doing it less powerfully. It'd still be hard to do. It's basically 100 feet per second. It's really fast. So power is how quickly you do work. Okay, so now we're getting some simple definitions. Remember how hard it was to come up with a definition for energy and work and power on? Yeah, we leave it to our physics brothers and sisters to get to the core of this for us. What unit of measurement do we use to tell us how powerful a car engine is?
Horsepower.
Horsepower. That's a real thing. That's a real unit of power. Horsepower. Another unit of power is something called the watt. You guys have heard of a 100-watt light bulb, right? That's how powerful your light bulb is. You guys know that a 100-watt light bulb is brighter than a 40-watt light bulb, right? And I don't know if 746 watts means much to you. I don't know if you guys ever been on one of those exercise bikes that do watts. Well, I can tell you, like Tour de France riders, they can ride at 300 watts for several hours. And when they sprint, they might hit 1,000 watts for a few seconds. So 746 watts sustained, that's a lot of power. That's not something a human's going to be able to do very easy. But a horse is a big, powerful animal, right? Okay, this really sort of puts it into perspective. So imagine that you're standing on top of a building with a rope, and at the bottom of the rope is a 55-pound weight, okay? You guys can lift 55 pounds, but, hey, you know, they're pretty heavy, right? You got to be a pretty big, strong man or woman to just pick up 55 pounds easy and just run off with it, right? 55 pounds is, you're going to feel it. You jam your suitcase full, right? Go to TSA, you got to keep it under 50 pounds. A 50-pound suitcase is a beast, right? That's why they charge you more when you're over that, because those poor baggage handlers got to deal with that. So think of standing on a roof, right, with a rope, and at the end of the rope is one of these jam-full suitcases, right? A horsepower is equivalent to raising that 10 feet every second. So think about trying to pull that rope up fast enough to lift that suitcase up 10 feet every second. You know? big strong dude or dudette might be able to do it for a second or two, right? I'm pretty sure I couldn't do it for a second. You know, maybe if I put it over my shoulder and just ran with it, I might be able to do it for a second or two. But even that's hard. To go 10 feet in a second, dragging a 50-pound suitcase, that's not easy, right? So that's how strong a horse is. I just saw they're making an electric Mustang car that's 840 horsepower. That's impressive, you know? So that's the kind of numbers we're talking about. All right, I want you to think about types of energy. We've talked about a couple of types already, but just list maybe 5 or 6 sources of energy. Something that enables you to move something. Okay, I'm not going to ask you for your list, but whatever you write down, you can see sort of where it fits in the energy types that I'll show you here, okay? So this first energy type is something called chemical energy. It's energy from chemical reactions. Atoms forming compounds or atoms in compounds that are breaking apart. Typically what this means from a practical standpoint is burning things. Humans love to burn shit. We burn things all the damn time. And then nature manages to burn itself up too, which is doing a really good job around here right now. And when you burn things, what happens is you usually take oxygen and combine it with some of the substances in whatever the fuel source is, wood, fossil fuels, crap. And you end up with heat and then byproducts like CO2. So it's a chemical reaction that takes the cells in something like wood, combines with oxygen, you get heat plus CO2. And we use this a lot. Humans have been using this fuel source since we were cave people, you know? Burning things. Gives off heat. Heat is energy. You guys know what those photos are? I took those photos in India. As you drive along the roads, you'll see stacks of this everywhere. And sometimes you see them on people's houses. Think you know what it is? It's crap. It's cow shit. And what happens is, and I saw this a bunch of times, is, you know, some farmer will bring up a whole truckload of cow crap and dump it right next to the road, and then the local women will gather around the big steaming pile of cow shit, and they'll pat out these patties with their hands, make these perfectly round patties, and then put them in the sun to dry. And then the villagers come up and grab 5 or 6 of these every night, bring them home, light them on fire, and that's what they use to cook, to heat their homes. Yeah, they're cooking all that lovely, beautiful, fragrant Indian food over piles of dried up cow shit. And it works great. Except the byproduct is CO2. And people a lot of times get CO2 poisoning, just like they do in homes that are wood burning or whatever. So we use this. We burn wood, we burn crap, we burn fossil fuels. When we talk about burning things, we're talking about chemical energy. Okay? This is one of our primary sources of energy in the world. That's why we're having problems with climate change, because everything we like to burn is carbon-based. And the byproduct when you burn carbon-based stuff is CO2, which goes in the atmosphere, retains the heat in the atmosphere, and screws up our weather, which is part of the reasons why we're having these stupid fires too. Now, one interesting thing about energy is that it commonly transforms from one form into another. So chemical energy is actually the energy in the bonds, okay? It is stored in the bonds of the crap or the oil or the wood. And after it goes through this chemical reaction, that chemical energy turns into heat, a fire. Burning cow dung, burning gasoline. And the byproduct of all that chemical energy is heat. You can also create heat without chemical bonds being broken just by rubbing things together so that you get friction. And one thing we know about heat, something we talked about first week of class, is that heat makes atoms move faster. When atoms move faster, they take up more space. And that expanding, let's say, air, let's say you heat the air up, that expanding air can be used to do some work. That's how engines work. The chemical energy in the gas is released as heat. The heat then expands rapidly and pushes a piston. That piston can then turn a crankshaft, which turns your wheels, which allows you to go. So you start with chemical energy, turn it into heat energy, and then that heat energy will expand air and do some work for you. Energy from mass, this is the big one. This is Einstein's contribution to humanity, was figuring out that mass, think about that atoms themselves can be turned into energy. And you've probably seen the equation, E equals mc squared, right? Everybody's seen it. Not a lot of people know what it actually means. But it means you can consume mass, the m, and create energy. You can take an atom and make it disappear. And the result is energy. And a lot of energy, because that little c there, the c squared, the c is speed of light, which is an enormous number. And when you square an enormous number, you get an enormouser number. So it means just a teeny tiny bit of mass can create a ridiculous amount of energy. So think about the mass in, say, a cell phone. It's got some mass here, right? If you took all this mass and converted it all into energy, made the cell phone disappear, and instead had all the energy that could be created with it, it would be enormous. It would be ridiculous. So as long as we have mass, we have a potential source of energy. Problem is we don't understand it well enough to release it very well. We know this happens in the sun with nuclear fusion. Two hydrogen come together to create a helium, but a little bit of mass is lost during that and transformed into energy. And look how much energy the sun gives off. And we do this now in nuclear reactors. We know it well enough that we can make some energy with it, but we don't understand it well enough where we can always do it safely. I mean, think of a nuclear bomb. That's exactly what happens during a nuclear bomb, is that some mass is consumed and this tremendous blast of energy is given off. So there's your conversion for speed of light, 671 million miles an hour. It's a pretty big number. Square that. So bottom line, a little bit of mass changed into energy is huge. And we have stuff all around us. Any potential mass could be used. We end up using hydrogen for fusion and things like thorium and uranium for fission, where you break stuff apart and consume mass. But bottom line, if you have mass, you can create energy from it. We just don't know how to do it real well yet as humans. But we're getting better. And again, it's the basis for nuclear energy. Nuclear energy is amazing. I wish we would use more. Because there it is right there. There's the end of all of our energy needs right there. But we haven't figured out how to do it safely. The byproducts are terrible. They're toxic. They're deadly. If you lose control of the process, you have a nuclear detonation and people die. It's dangerous. So we're not to the point yet where people feel comfortable enough going to this full bore, and for good reason. I certainly understand the angst about doing more nuclear energy. But at some point, we'll get better at this. Kinetic energy. Energy of movement. If I chuck this hand sanitizer bottle at your face, you think it has energy? If you don't, just let it hit your face and then tell me then, right? Clearly it has energy. And if I wanted to have more energy, what would I do? Throw it harder or have more of it, right? You know, if I chuck a styrofoam peanut at your face at 5 miles an hour, if I chuck the same size ball bearing at your face, right? Gonna hit with. So there's different factors that go into this, right? Well, physicists again have figured this out. Anybody know the equation for kinetic energy? You may have had it in a science class. Kinetic energy is 1/2 mv squared. 1/2 the mass times the velocity squared. So the heavier something is, the more kinetic energy it's going to have. The faster it's moving, the more kinetic energy it has. So heavy, fast-moving things will have a lot of kinetic energy. The good thing is that if you go outside, there's a lot of stuff outside that moves. The air moves all the time. If you go to ocean environments, waves move all the time. And a real reliable source are tides. I mean, you got the oceans that rise up and go down twice every day. Think about the mass of the oceans. It's enormous, right? You get that much mass moving, that's enough energy for humans to do everything they want to do. Where do most people on the planet live? Coastlines, where you have wind, waves, and tides. And yet, if you go to coastal communities, what are they using as an energy source? Gasoline, electricity from coal burning. And yet, right out the door is all this stuff that moves. But we're getting better at this. The problem is that we've had a hard time storing this kind of energy for when the tides are low or the waves are small or the wind is light. But we're getting better at that too. Okay, potential energy. I like talking about this one. potential. All right, let's say I had a bowling ball. You guys have all seen bowling balls. I'm going to put a bowling ball right here, okay? Right on the edge, barely balanced. And I'm going to ask you to come up, lie on the floor, and put your head right below the bowling ball. Are you happy about that situation? But the bowling ball isn't moving, right? Let's say the bowling ball was only 6 inches above your head, okay? Still not very happy about that, right? What if it was 20 feet above your head? Bowling ball's the same, right? Your head's the same. What's different? The height, right? So, potential energy is kind of interesting because as of itself, it's not doing anything. That bowling ball's just sitting there, right? It doesn't have any kinetic energy. What if I just give it a little flick? Then what happens? Falls off the edge, right? Then it starts moving towards your head, right? What happens to the speed as it gets closer and closer? It's accelerating. It's going faster and faster. So the higher up it starts, the more time it has to increase speed, right? That's why you don't like it 10 feet above your head, right? A couple inches, it's like it's not going to gain much speed. Just going to flop over. It's still going to be uncomfortable. You know, dropping a bowling ball an inch and hitting the top of your head wouldn't be very pleasant, but do it from 10 feet and you're dead, you know? So potential energy is the density. Think of that bowling ball being made of styrofoam. Drop it from 10 feet. I'll let you do that. I'll let you drop a styrofoam bowling ball from 10 feet on my head. I could take that. But if that bowling ball was made of metal, lead, it's going to be bad, right? Gravity obviously plays into it. Drop it from 10 feet on Earth, drop it from 10 feet on Mars, you can get a much different result. And the height. Because the higher up it is, the longer it's going to take to hit the ground, the more time it's going to have to accelerate. So it's going to be moving faster with more time. So what happens is potential energy gets turned into kinetic energy, right? And think about it. As the ball falls, right, what's happening to its potential energy as it falls? The height is getting less, right? So the potential energy is less and less, right? What's happening to kinetic energy as it falls? It's increasing, right? So you start with potential and no kinetic, right? And then as the ball falls, the potential drops and the kinetic goes up. And by the time it hits you, it's not going to have any potential energy, but it's going to have a whole lot of kinetic energy. So that's one of the things that we're going to try to do as humans as we invent new alternative energy sources, is try to look for sources of potential energy and how we might convert it into kinetic energy and vice versa. One of the interesting things that I've seen is we have a hard time storing kinetic energy, right? But what I saw is a windmill, and what the windmill would do was it would create enough energy to lift giant rocks up during the, let's say during the day, when the wind was blowing strong. And then when the wind stops blowing, you know what they do? They let the rocks go down, and it turns a turbine and creates energy. So they're using potential to store kinetic, and then the kinetic is used as an energy source later. And I'll give you some more examples if that didn't make sense as we go through this. Electric. We use electric energy a lot. And we're going to use more and more electric energy as time goes on. Electric energy is pretty interesting. We use it a lot, especially for non-transportation needs. Just think of how many things you plug in, right? Refrigerator, freezers, electric ovens, electric water heaters, razors, computers, cell phones. But it's even creeping into Transportation, right? We're seeing more and more electric cars, more and more hybrids. Electric engines have a lot of design advantages. They can create far more torque than a combustion engine. So it is creeping into transportation, and in fact, I would suspect, by the time you're my age, we're not going to see any internal combustion engines doing much work out there. It's going to be mostly electric, unless somebody comes up with a radical new idea, which is never out of the question. You guys have probably heard of Elon Musk, entrepreneur, invented PayPal, Tesla, electric cars. He's all in on electric cars being the future. And he said, the biggest technology challenge with electric cars is storing enough electricity in the batteries to give you the range that people desire. If you can only go 20 miles before having to recharge your car, that sucks. You want it at least on par with a full tank of gas, several hundred miles. And our batteries are getting to that point, but they should be a lot better. And what Elon Musk has said is, he says, I've hired every battery engineer in the world to work for me. He goes, we will figure this out. Battery potential, he said, right now is doubling every 2 years. He said in about 15 years, batteries will be strong enough to do everything we need them to do. So he thinks there'll be a complete switch over in 15 to 20 years. Other people think he's overly optimistic, but I don't know. It's interesting. So battery technology is the big challenge, because that's what we need to store electric energy. It's hard to understand because you never really see electricity. You've seen lightning bolts and you've seen sparks, but electricity doing the work in your computer, you don't see it, right? Your computer's just on. The lights are on. You don't really see how this is working. So it's really hard for a lot of people to understand just what is electricity. I just know it comes out of the wall, it goes through wires. But now we have wireless charging, right? It's like, how the hell does that work? So it's getting to the point where the technology goes beyond sort of your common sense and trying to figure out how it works. It's just like magic, right? Most people think of electricity, it's just sort of magic. It happens behind the scenes. But I want you guys to understand a little more than that it's magic. It is officially a flow of electrons. And a flow of electrons is something called a current. There's a scientist a couple decades ago, or a couple centuries ago, Faraday. Faraday should be right up there with Nikola Tesla and Albert Einstein and all the other great scientists, but you don't hear enough about Faraday. But Faraday was brilliant, and I'm not sure how he figured this out. But without Faraday, we would not have modern society. We would not have electricity as a usable energy source without his ideas. He discovered, I don't know how he discovered this, I'm going to have to look into it, but if you pass a magnet near a coiled wire, you make the electrons in the wire move. So he coiled up a whole bunch of copper wire, and he moved a magnet around it, and it created an electrical current. And that's what we do today. You guys have heard of turbines? A turbine is a moving thing. It's usually something that spins. You've seen windmills, right? You've seen turbines maybe in water where the water will move it, like a water wheel, right? That is exactly what's happening. So what you have is a coiled wire in the middle, and then the windmill or the water wheel or something spinning moves magnets around the outside of it. And that makes electricity in your current. It's the coolest thing. So all you need is to spin something. If you can spin something, you can create electricity. You put a big wad of coil wire in the middle, you put some magnets on whatever's spinning, and you let them spin around the wire, and the wire makes electricity. And you can funnel that off in all different directions. So a coiled wire and magnets, and spin the magnets, and you got yourself electricity. It's pretty cool. And we'll come back to that idea. I'm going to have you guys design some turbines and try to figure out how to maybe harness tides. How can I take tidal power, put some turbines in there, and make electricity with tidal power? I'm going to have you guys do that. Maybe next class. We'll see. Okay, so we have those various forms of energy, right? What we do as humans is we generally transform other forms of energy into electricity. Because think about it, in order to make a turbine work, you have to have something spinning, right? You have to have something moving. That's kinetic energy. So under Faraday's little model here, you have to have some sort of kinetic energy in order to produce electrical energy. Now the way we normally do it, probably the easiest way to understand it would be a windmill, okay? So you got the wind, it's a form of kinetic energy. It hits the blades of the windmill. The kinetic energy from the wind creates kinetic energy in your blades. So you've got moving blades. The blades are moving in a circle. They're carrying magnets around a coiled wire. So the kinetic energy from the wind is transferred into kinetic energy in the windmill, which eventually creates electricity as the magnets move around that coiled wire. So we can do it with a windmill, but the way we normally do it is we burn crap. Because we like to burn stuff. And we've been burning stuff a long time, and we're good at burning stuff. So what we do is we burn wood or coal, most likely, or maybe liquefied natural gas. So you're starting with chemical energy in the coal or wood or liquefied natural gas or oil. When you burn it, heat is released. That heat can be used to, let's say, heat water to the boiling point. When water boils, it expands rapidly. That expansion is a form of kinetic energy. And that expanding air can move a turbine. It can spin things. And that spinning magnets around a coiled wire can produce electricity. Or we can go to a hydroelectric dam and let water move past turbine blades, and it'll spin like crazy and produce electricity. But the whole idea is to get something to spin. And people are getting pretty creative with it. They're developing little tiny turbines that you can put in sewers. So every time you take a flush, there's actually going to be a turbine in your sewer, and it spins as all the waste products go through, and that creates a little electricity. They're doing that out in Portland, Oregon, actually. Or you can put turbines in a stream. You can do it big with a dam, but people are finding out that, we don't even need a dam. Just a moving water. We can just throw these little turbines out in a moving water, and they can create electricity. And if we do it in enough places, maybe we have enough to really power things on a big scale. So this idea of energy transformation is something we do a lot. The problem is that there's a another physics concept that comes into play. And it's like every time you move or transform energy from one to another, you lose some of it. Think about wind interacting on a windmill, right? The wind hits the windmill, but the windmill doesn't harness all the energy from the wind. There's inefficiencies, right? There's friction. Trying to get that thing to spin frictionless. The less friction you have in your machinery, the faster it spins, right? The faster it spins, the more electricity. So you lose some to friction. Friction causes heat. These things heat up, and that's just a loss of energy along the way. In India, I've talked about this before, their power lines are so efficient. As electricity flows through power lines, they get hot. That's losing energy. So they lose enough energy that basically a quarter of all energy they produce there is lost to inefficiency. And that's one of the big goals now, is to try to make turbines more efficient. Make them spin easier so that we can create more electricity with less loss. There's some forms of turbines right there. You guys have seen windmill turbines, right? And you've probably seen them on land, but you find them a lot in offshore areas as well. They are being used to harness tidal power. A lot of them are sunk into the seabed just offshore, and as the tides come up, turbines spin one way. As tide go up, they spin the other way. So that's what you're seeing sort of there in the upper left. In the lower or upper right. In the lower left is a turbine in a sewer. So as water or wastewater or stuff moves through, it spins that turbine and creates a little bit of electricity. Bottom right shows how a hydroelectric dam works. What you're doing is creating potential energy, right? So that water can fall down and speed up, and it's released from the outlet, but in between you stick some turbines. And a lot of these turbines are huge. If you've ever seen turbines in a dam, they're enormous, but they produce a boatload of electricity. So this is kind of what we're thinking about with alternative forms of energy. Because we like electric. We use electric for everything, and now we're starting to use it for transportation as well. So how can we make electric energy? That's where the future lies for all this. All right, I'm going to leave at that because this next one's going to take more than 5 minutes. And see you guys all on Thursday.